part 1 of Unit 6, Lesson 4, Applying Properties of Definite Integrals. So in this section, we're going to move beyond just creating rectangles and having finite sums. And we're going to start talking about the integral itself and what happens when we look at the limit as the terms become infinitely small and the number of rectangles approaches infinity. So we're going to look at how we can do this geometrically still, where we have negative values, which we've already done a little bit, which means we're below the x-axis, as well as positive values and what happens with 0. Some of those we've already worked with already. And one of the first things we worked with in the last section was negative area. At times we will integrate functions that go below the x-axis. Here are a few pointers when that happens. Area below the x-axis counts as negative area. The total area between A and B for some curves is really a net area, where the total area below the x-axis is subtracted from the total area above. Now that's not always true, but it is true in some cases, and we're going to look at those first, and then we'll talk later about when it is not true. Okay, so here is our Leibniz notation for the definite integral. Greek letters of summation become Roman letters in the limit. So the notation of a to b f of x reads like this. So if you read to this out loud, and I've been doing this, this is the definite integral from a to b of f of x with respect to x. And we need that part. That's where the dx comes in. That tells us what our independent variable is, our variable of integration. Because we're going to see, and I think I've mentioned this previously, excuse me, that we're going to see functions where we have more than one variable, so it's important to know what we're integrating, what variable. Okay, so breaking this down into its pieces, here's what we have. Sorry, I have a dry throat. All right, so the first arrow here, this is our upper limit. That S thing is the integral itself, and the A is the lower limit. There's our function, which is known as the integrand, and don't forget it is also our derivative of whatever function we are working with. And then the dx is our variable of integration. And so this whole thing is our definite integral. Okay. So, and what do we use our definite integral for? It's used to find the net area or if you want to think about it from what we've done in previous units, the distance traveled, because remember we were looking at velocity graphs and then we use the area under those graphs to find the distance traveled. And this area is bounded by the x-axis, the function, and two vertical lines, which come from our limits of integration. So we have x equals a and x equals b. Okay, so moving on from here, let's do a little example. Use the graph below to evaluate each of the following. Note that the graph of f of x consists entirely of line segments and a semicircle on the interval from -8 to 13, and including the endpoints. Okay, so let me just make this a little smaller so we can get some of these in, and I'm going to leave a few of these for you to do on your own. Okay, so letter A says we want to integrate f of x from 0 to 7. So we can find the area, and we have a giant trapezoid here. So we have a base here of 7. We have another base here of 3. And then we have a height here of 4. Now, if you want to break that up into 3 smaller pieces, that's fine too, if you want to do that. So you have a rectangle here. Let's do that, because I know later on we're going to need to piece this up into a couple pieces. So let's do it this way now. So these two triangles will be identical, so they're both going to have areas of 4, 1/2 base times height. And then we have this rectangle in the middle, that's 3 by 4, so that's going to be 12, like that. Okay. And we might have to change this a little bit based on what we're looking for. So our area is going to be that the total of the area we just found, which is going to be 12 plus 8, which is 20. Okay, from 0 to 13, now we have 0 to 7, we just have to figure out the area from 7 to 13, and since it's below the x-axis, we are going to subtract it. So I, again, just did it in one big piece here, and I have a height of 3 here, and then I have 2 bases of this trapezoid. This trapezoid is 6, has a base of 6 on top, and 3 on the other side. So I'm gonna, this area is going to be 1/2 of 9 times 3. So it's going to be half of 27 over 2, which is 13.5. Okay. So what we're going to do is we're going to take our area from 0 to 7 and subtract from it the 13.5, so we get a net area of 6.5. Okay, so the only difference with the next one and the next two is we've talked about these a little bit is, well, the next one's fine. I was thinking that was a positive 6 there. So I'll leave that one for you guys to do. And letter D, let's talk about that one. In letter D, what we have is we're going from the singularity of a point and we're going nowhere. So this will have area 0 because we don't even have a linear measurement there. A point is one-dimensional. Now the next one, though, what you notice is the limits of integration are backwards. So we're going to be going towards the left. So really what we're going to do is we're going to think of this as the opposite of what we already figured out in part A, because we're going to be moving this way towards 0 in the opposite direction. So the answer to letter E is going to be negative 20. All right, I am going to pause the video here for a second and let you guys do letters C, F, G, and H. Okay, hopefully you paused the video and took the time to figure those out. Here are the answers to C, F, G, and H. And in case you're wondering why H does not exist, if you look at -6 here, you actually have a cusp because you're going from a straight line to a curve. So you have like a corner there. So we are not going to have a derivative there. Okay, so finishing this section up, f double prime of -6. So if we look at the graph at -6, what we see here is as we're approaching -6, we have a linear rate of change there. So if you take the derivative of that derivative, okay, that would be the second derivative, we're going to get 0. So let's just summarize that here. So what we have going on here is that knowing that f prime is constant because it's a linear function, f double prime is 0, since the derivative of a constant is 0. So the average rate of change over 0 to 5, we're just going to get those 2 points and find the average rate of change for that. So at 0, we're at 0, 0, and at 5, we are at this point here, which is 5, 4. So those are the 2 points we're going to use to find the average rate of change. So our average rate of change is going to equal 4 minus, that doesn't look like a 4. Let me write those 2 points here. So at the origin, we're at 0, 0, and at 5, we're at a height of 4. So we're going to do 4 minus 0 over 5 minus 0. So we get 4/5. Okay, and then we want to see if this is true or false. So we want to know if we add the area from 0 to 2 to the area from 2 to 4, do we get the area from 0 to 4? So let's take a look here. So this is saying if we take the area from 0 to 2 and add to it the area from 2 to 4 here, do we get this total area here from 0 to 4? I guess I went a little further with this. Let me fix that just a little. It would just be here, these two pieces here. So will that give us, is that a true statement? And the answer to that is yes, of course, because we're just going to add the pieces of our area. So that is a true statement. Over which areas of or values of x is f of x not differentiable? So it's going to be everywhere we hit a hard corner or a cusp, and there are several of those. Let me clean the graph up here a little bit so we can see the x-axis. So for that one, we will see that we have a corner here. We already talked about that at -6. We have one at 0 where we go back from the semicircle to the line. We have a hard corner there at 5, at 7, at 8, and at 11. So there's a lot of points on our graph where f is not differentiable. So let's go ahead and write those all down again. So we have at x equals -6, 0, 2, 5, 7, 8, and 11. Okay, so as I've said before, we've been flirting around with some of these properties here, and we haven't formally defined them. So we're going to define them now. So what we're saying is we have a definite integral on the interval, the closed interval a to b, and we're going to specify that a is less than b. However, to extend this definitions where a is equal to b or a is greater than b, we're going to look at it in this way. We've used the first one several times. We're assuming that f is defined at a, then the integral from a to a is going to be 0, because that's, as I said, one-dimensional, and it's just a point. We have no area under a point. The second one is if a is integrable, I can never say that when I want to, integrable on a to b, then here's another property we've used. If we change the order of integration, it's going to equal negative the assumed order from a to b. So those are opposite of each other. The next one is that this is another property we've done, which is the additive interval property. If f is integrable on 3 closed intervals determined by a, b, and c, then we can break that into 2 smaller intervals and then add them together. Because remember, we're just adding areas, so areas add together. And then finally, especially on a closed interval, because they'll be touching. And then the other ones that are here are the fact that we could have a constant k. Then if we're multiplying a constant times a function, that's not going to affect the integration. We can just pull that out and integrate our function as we did before. The next one is if we do just integrate a constant, we're just going to have those this is just going to become k times the difference of our limits of integration. And then finally, if you're integrating several functions together, you can, and they're being added or subtracted, you can do the integration separately for each function and then either add them or subtract them. Okay, so let's work with these properties in example 2. So we're supposed to use the properties to evaluate each of the following, given these following integration values for f, g, and h. So in the first one, if you notice, we are going from B to A. You're going to have to start paying attention to that instead of from A to B. So what that means is we actually want the negative value of the integration of g from A to B dx. So we're given that that is -3, so we're going to have a -3. So we're going to get a +3. The next one is we have a constant. So what we can do is we can factor out the constant outside of the integration. And then we can multiply that times our integral. And in this case, we're told integrating f from A to B is 8. So we're going to get 16. Okay, letter C, we're integrating a constant. So this is going to become 5 times b minus a. And since we don't have any values for b and a, we're going to have to leave it like that. That'll be our final answer. And then for letter D, we're going to break this up into pieces. So we're going to integrate from a to b of 5 plus the integral from a to b of g of x dx. And this is going to give us our 5 times b minus a. And then we're going to add to it our value at g. So this will change that to -3. And then the next one, we're subtracting two functions. So we can separate those into separate integrations. So separating f of x, and make sure that each of them has their own dx when you separate them. That variable of integration is super important. So we are going to have then f of x is 8 minus h of x is 5 over 2. So that's going to give me 16 over 2 minus 5 over 2 is going to give me 11 over 2. And then finally, this is the property where we're breaking the interval up. We're going from a to 4 and then from 4 to b of h of x. So that would be the same as going from a to b of h of x dx. So this just has a value of 5/2. Okay, so I am going to stop here for this part of the video, and in the second video will be more practice and talking about even and odd functions.